In this video, we're going to be looking at how to graph polynomial functions, and to do that, we're going to first discuss something called end behavior, which is really just looking at how a function behaves for very large and small values of x. So this tells you what a polynomial does for large and extremely small values of x. So let's take a look at the different cases, and there's 4 different cases. The first one is when the leading coefficient is positive. The notation we would say is a sub n is bigger than 0, and the degree is even. We always call that the degree n. So the end behavior would look like the following. Before we do that, let me give you an example. If I give you a polynomial like f of x equals, I don't know, let's do 7x to the 8th plus 4x squared minus 1. This one is written in standard form. The degree n is 8, which is an even number. And the leading coefficient we would call a sub n is 7, which is positive. If I have those 2 cases, what's going to end up happening for very, very large values of x, and let's pretend, on our graph here that I'm way over here, let's say at just even the number 10. If you were to plug in 10, by far, this term is going to get super, super big right away. It would be 10 to the 8th power times 7, whereas this is only 10 squared times 4. This is the most influential on what's going on. So 7 times 10 to the 8th power is going to be a huge number. It would be a point way, way up here. So what I know for end behavior is this polynomial is going to end up going up towards positive infinity, up and away like that. Now, if I plug in a really, really small number for x, like negative 10, when I plug in a negative, let's look at this real quick. If I plug in a negative 10 and I raise it to the 8th, would you guys agree that this is still going to be a positive 10 to the 8th, right? Because a negative to an even power is going to be positive. So it'd be 7 times this 10 to the 8th number, which is still huge. It'd be something way, way, way up sky high. So I know that when I plug in really, really large negative numbers, which I should really say are really small x values, the function is going to go up towards positive infinity. Now, the reason why I'm leaving the center here blank around 0 is end behavior does not tell you what's going to happen around the origin. It's only good for very large and small x values. You'll see when we graph, when we plug in numbers like 0, 1, 2, -1, -2, -3, a lot of different things can be going on, and it doesn't necessarily, it's not necessarily influenced by the degree or this leading coefficient. So let's leave this blank in the middle. We'll have to plug in numbers to see what's going on there. So that's one case. Let's look at the second case. When the leading coefficient is positive still, so we still have a positive leading coefficient, but now the degree is going to be odd. So n is odd. Then the end behavior is going to be a little different. Let's get an example and we'll kind of analyze it a little bit. Let's look at f of x equals, I don't know, let's do 2x to the 5th plus x minus 5, let's say. Okay, here my degree n, my highest exponent I see is 5, which is an odd, right? That fits what we're saying. My leading coefficient a sub n is 2, which is fitting a positive. It's positive. Now, when that's the case, if I were to plug in a really big x value, again, let's just kind of use 10 for right now. If I plug in 10, this first term really gets big. It would be 2 times 10 to the 5th. Oops, let me rewrite that. It would be 2 times 10, raised to the 5th, which is a huge number. It's something way, way up sky high. So once again, the graph, as I move to the right, would take off going upwards to positive infinity. That would be a really, really big x value. or y value, excuse me. If I plugged in negative 10 for x, that means this first term would become 2 times negative 10 raised to the 5th. But this is a little different than the one above. If you take a negative number to an odd power, doesn't that stay negative? It would be a positive 2 times a really, really big negative number. That would be negative 1 with 5 zeros. Geez, what is that? That's 100,000, negative 100,000. But if you multiply it times a positive 2, it's just negative 200,000. So if you were to plot that, that's way down low down here. Now the graph is going, downwards like that. So the end behavior in this case looks like this. It goes up and to the right and down and to the left. There's a couple more cases we're going to look at on the next slide, starting with now leading coefficients that are going to be negative. So if the leading coefficient is negative, we would say a sub n is less than 0. And let's look at when the degree is even, or n is even. Then we'd have n behavior that would look like this. Let's use an example. Let's do f of x equals negative x squared plus 2x minus 5. Keep it simple. Let's look at a polynomial that we're familiar with. This is a quadratic. You guys know that a sub n, the leading coefficient, is negative 1. And we've talked about how that means it opens down, right? Here we're just going to say it's negative. That's the important thing. And the degree is 2. That's even. So it fits the case. Degree even, a sub n is negative 1. It's negative. You guys know that if you plugged in a really big x value like 10, you'd have the opposite of 10 squared, which would be negative 100. That would be something way down low. End behavior would be going down like here. If I plugged in negative 10, well, you'd have the opposite of negative 10 squared. The key is, when you raise a negative to an even power, it turns positive, but there's a negative in front, making it still negative 100, right? So you're going to end up still with something really far down low. So as you plug in small numbers of x, it's still going to give you really, really small outputs for y down low here. So, and if you think about it, you knew this was a parabola. That would just be a U-shaped graph opening downwards. So it kind of fits the end behavior that we have there. I just didn't connect the middle. Let's look at one last case. When the leading coefficient is negative, so a sub n is less than 0, and the degree is odd, or n is odd. An example might be the following. Let's do f of x equals negative x to the third plus 2x minus 5. Here I have an a sub n value that's negative 1. That's negative. That's the important thing here. The leading coefficient's negative. The n value, the degree, is 3. So it fits that case where it's odd. Well, let's see what goes on here. If I plugged in a very big value of x like 10, would you agree we're going to get the opposite of 10 to the third? That would be just negative, what, 1,000? So that would be way, way, way down low down here. That's going downwards, right? If I were to plug in a number like negative 10, I'd have the opposite of negative 10 to the third. Now, key here is when you raise a negative to an odd power, it's going to stay negative. So that would be the opposite of negative 1,000, which is really positive 1,000. A negative times negative would make a positive. So I'd end up with something up here, a really big positive number. So it would go up, up, up in a way like that. So the end behavior here kind of looks like this. These images for the end behavior are going to be important, and knowing these cases is going to make graphing life a lot easier. I'm going to show you 2 examples of how to graph, and then I'm going to have you guys try one on your own. Now, let's do this first example together. The first thing you're going to do is make a table of values and plot corresponding points. Only plot as many points as you need until you recognize that the graph is following its end behavior. One thing that I'll do maybe first is even look at the end behavior right away. Let's think of what n is and what a sub n is. n is the degree, it's 3, which is odd. A sub n is the leading coefficient, which is just 1, which is a positive. Now, if you go back in your notes and you look at the case where a sub n is positive and odd, I think you'll remember the graph went something like this. It went up and away to the right, and it goes down to the left like that. So I don't know what's going on around here, but I do know that my graph will end up going up to the right and down and to the left. To figure out what's going on in the center, that's what we use this table here for, guys. So let's see what we're going to get. There's a couple ways to fill out the table. You can use either direct substitution, or we can use synthetic substitution. A lot of students kind of become a fan of synthetic substitution once they get the hang of it. So let's go ahead and use that. If I wanted to plug in -3, I'm going to put it in the box. I'm going to write the coefficients 1, 1, -4, -1 down. And I'm going to drop down the 1, multiply to get -3, add to get -2, multiply to get 6, add to get 2, multiply -3 and 2 to get -6, add, and I get -7. So when I plug in -3, I get out -7, which I can plot. I believe, let's see if I can get it on here nicely, -7 would be right here. So that's my first coordinate. If I were to plug in -2, I use the same coefficients, 1, 1, -4, -1. Drop down the 1, multiply, I get -2, add, I get -1, multiply, I get 2, add, I get -2, multiply, I get 4, add, I get 3. So that means when I plug in -2, I get +3. So when I plug in -2, I get +3. That's way up there. If I were to plug in -1 into 1, 1, -4, -1, drop down the 1, multiply by -1, I get -1, add, I get 0. If I multiply, I get 0. If I add -4 and 0, I get -4. If I multiply, I get +4. If I add, I get 3. So when I plug in -1, I get 3 again. So I get, let's see if I can draw this point. If you plug in 0, I don't know if we need to do synthetic division for that. You know, all those terms wipe out. You get just -1. So 0, -1 is right there. I'm going to go ahead, if it's okay, guys. I'm going to erase some of my, oops, wrong tool. I'm going to erase some of my work here so I can stay on the same screen and not lose it. I'm going to kind of plug in a couple more values here. You can always rewind, right, and check out how I did those other ones if you missed it. If I plug in 1 into 1, 1, -4, -1, I get 1, add, I get 2, multiply, I get 2, add, I get -2. If I multiply 1 and -2, I get -2. If I add, I get -3. So when I plug in 1, I get -3. So 1, -3 is right there. If I plug in 2 into 1, 1, -4, -1, start off with multiplying 2 and 1, I get 2, add, I get 3, multiply 2 and 3 to get 6, add, I get 2, multiply to get 4, add, I get 3. So when I plug in 2, I get 3. Plug in 2, I get 3, oops, right there. And the last one I'm going to plug in is 3. If I plug in 3 into 1, 1, 1, -4, -1, drop down the 1, multiply by 3, I get 3, add, I get 4, multiply, I get 12, add, I get 8, multiply, I get 24, add, I get 23. That one's kind of tough to graph on here since I only go up to 10, so 23, I mean that's just off the charts, way up high, somewhere off the screen there. Now, the key now is it almost looks like a crazy scatter plot. It's like, what's going on? Guys, keep in mind your end behavior. It starts down very low, and at this point, right here, that was the lowest value I plugged in for x, right? That was when x is -3. If I were to keep on plugging in like -4 and -5, this would just go down and down and down. It's following the end behavior. From here, I have to carefully kind of connect the dots, from left going right with without I want to get rid of that circle, without kind of making any sharp turns. So from here, the next point I want to go up to is this guy. Now I don't want to just hang a hard right and do a corner. These polynomials are smooth functions, so I would have to make a short turn and come back down and then hit this point next. Once I hit this next coordinate here, I have to turn around. I'm going to try to make it a smooth turn, and then I would hit this guy, and then remember it goes up, up, and away to 23, right? I'm just going to put an arrow because it's following that end behavior where it goes up to infinity. Notice how I put my arrows to show that it goes up, up, and to the right, and it goes down, down, and to the left. And in the middle, this is where it's critical that you evaluate those points correctly, because it will, I call it does a little wiggle in the middle. It's going to have some waves in there, and every graph could be a little different depending on what the numbers are. I'm going to do one more example before I'm going to ask you to do one on your own. Let's take a look at this guy. End behavior. The degree is even, it's 4. The leading coefficient is a -1, which is negative. If you go back to your end behavior, if the degree is even and the leading coefficient is negative, it goes down and down. Let's see if we can evaluate a few points to fill out a table. Let's start with 0. I'll show you a technique where you might be able to save yourself time by starting at 0 and working your way out. So if I plug in 0, actually that's going to be easy, right? If you plug in a 0 everywhere for x, I think you just get 0. So you get 0, 0. If we try to plug in 1, let's use synthetic substitution. If we plug in the 1, in the box it goes, the coefficients are -1, -2, 2, and 4. So we would drop down the -1. If we multiply, we'd get -1. If we add, we get -3. Multiply, you get -3. Add, -1. Multiply, you get -1. And if you add, you get 3. So when you plug in 1, you get 3. Let's plot that point right there. Let's try plugging in 2 into -1, -2, 2. Oops, you know what? Mr. Schulte's made a mistake. Very good thing that, actually I'm kind of glad I made this mistake so we can check it out and find out where we went wrong. When you guys do synthetic substitution, something I forgot and a lot of students forgot, or will forget, is any missing terms. Guys, this is in standard form. You have your x to the 4th, your x cubed, your x squared, and your x. What's missing? The constant term is 0. You even need to include the 0 when you're doing synthetic substitution if that constant term is not there. That's what I forgot. I should have tacked on a 0 here. That's going to make a difference. Let's try this again. I'm glad we caught that. If I multiply, I get -1. If I add, I get -3. If I multiply, I get -3. If I add, I get -1 again. If I multiply, I get -1. If I add, I get 3. Now if I multiply, I get 3. And if I add, I get 3. Okay, turns out it stays the same, so we kind of lucked out. If I get 2, I'm going to do -1, -2, 2, 4, and 0. And actually, I think maybe when you have a constant of 0, maybe it doesn't make a difference. Let's see, if I drop down the -1, 2 times -1 is -2. If I add, I get -4. If I multiply, get -8. If I add, I get -6. If I multiply, I get -12. If I add, I get -8. If I multiply, I get -16. And if I add, I get -16. Yeah, it kind of makes a difference, right? If I didn't have the 0 there, I would have ended with -8, but really it's -16. Guys, that's already starting to be a pretty low value, and it's following my end behavior. I kind of figured it was going to go downwards, right? And it's already doing that. I'm not going to waste my time plugging in 3. I already know it's going to be a pretty large negative number. So I can't even plot when I plug in 2. When I plug in 2, it's something way down low. Let's work our way to the other side, and if it's okay again with you guys, I'm going to erase a little bit of work so I have room to work to the left. Let's erase, 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 erase. Ain't the best thing in the world. Okay, here we go. If I plug in -1, and the coefficients again are -1, -2, 2, 4, and 0. If I drop down the -1 and multiply, you get +1. Add, you get -1. Multiply, you get +1 again. Add, you get 3. Multiply, you get -3. Add, you get 1. Multiply, you get -1. And I get out -1. So when I plug in -1, I get out -1. So approximately right there, right? Let's plug in -2, and I get -1, -2, 2, 4, 0. Drop down the -1, multiply, you get 2, add 0, multiply 0, add 2, multiply -4, add 0, multiply 0, still get 0. So when I plug in -2, I get 0. Now, I would still need to plug in -3 because I'm not quite following the end behavior yet. I know that it's going to end up going downwards, but that last coordinate wasn't a really large negative number. So I'm going to go ahead and plug in -3, and hopefully that's the last one I'll need to plug in order to make sure it's following its end behavior. Let's try -3. If I do, I get -1, -2, 2, 4, 0. Synthetic substitute, multiply, you get +3, add, you get 1, multiply -3, add -1, multiply 3, add, you get 12, multiply, you get -36. How did I get 4 plus 3 is 12? That's interesting. 4 plus 3 is 7. 3, let me erase this here, 3 times -7, or excuse me, -3 times 7 is -21. Still a pretty large negative number, but I just came up with the wrong one. -21 is finally following that end behavior. It's way down low. So when I'm doing this one, I'm going to start low, I'm going to come high, smooth transitions through these points, kind of a roller coaster up and then down. Now I kind of made, that wasn't a very good last section there. I want to make sure I don't go back and fail the vertical line test. I want to go kind of straight down. So I get this kind of M-shaped looking guy. Guys, this is unfortunately one of my longest videos ever. Apologize over that. If you would please try to do this one graph on your own, think of the end behavior, fill out the table, and see if you can get that as good as you can get it for tomorrow's class. Thanks for watching.